Welcome to the deep dive. We take complex ideas, dig into the source material, and pull out the knowledge you need right now. Today, we're diving deep into a sense most of us totally take for granted. Hearing.
Yeah, absolutely.
But it turns out it's fundamentally, profoundly linked to our long-term brain health.
And we're starting this conversation with, well, a real sense of urgency, actually, because the medical community is finding this incredibly strong evidence, concerning evidence, linking unaddressed hearing loss directly to a higher risk of dementia and, overall cognitive decline.
Wow.
So it's not just about, oh, I can't hear conversations well anymore. This is a major brain health issue.
Yeah, the scale of this is really what kicked off this deep dive for us.
Yeah.
I mean, hearing loss affects 1.5 billion people globally right now.
It's huge.
And if you needed a sign of just how massive and, frankly, underappreciated this whole public health challenge is, the World Health Organization, they estimate another billion people will be affected by 2050.
Another billion. That's just staggering. It really is.
So our mission for you today is to try and cut through some of that complexity.
Right.
We want to unpack the delicate mechanics of how we hear, explore what's actually damaging our ears, often silently.
And often way earlier than we think.
Exactly. And most importantly, give you some actionable, science-backed tools, protocols really, to protect your hearing.
And by doing that, protect your cognitive future.
Definitely. And all the insights, the protocols, the stats we're sharing today, they come straight from sources distilled from a conversation with one of the top medical doctors and researchers in otolaryngology.
A real expert in the field.
So let's unpack this system. Let's start with its architecture. How does hearing actually work?
Well, it's fair to say, isn't it, that we kind of treat hearing as the neglected cousin of vision.
Yeah, that feels right.
If your vision starts to go, you get glasses. Often restores you back to, perfect 20/20. Glasses are a tool. Sometimes they're even cool, a fashion accessory.
Right. But the words we use for hearing loss, they kind of tell the whole story, don't they? We don't have hearing restorers.
No.
We have hearing aids.
Aids, they just assist what's left. They don't bring back normal function.
So why is it so hard to restore? Let's get into the mechanism.
Okay. So sound waves travel down your ear canal. Pretty simple start. They hit the eardrum, that's the tympanic membrane, and make it vibrate.
Okay, so vibration's in the air, but then it needs to get into liquid, right? And that involves those tiny little bones everyone learns about.
That's exactly it. The smallest bones in your body, the hammer, anvil, and stirrup. Or, the malleus, incus, and stapes, technically.
Right.
These little guys amplify and transfer that mechanical energy, that vibration, across the middle ear and into the inner ear.
And the inner ear is filled with fluid.
Yep. Paralymph and endolymph. And once those tiny bones get that fluid moving, you hit this critical stage called mechanoelectrical transduction.
Okay, mechanoelectrical transduction. Sounds pretty technical. What does that mean in simple terms, and why is it so crucial?
It basically means turning physical movement mechanical into nerve signals electrical. That fluid movement inside the hearing organ, the cochlea.
The snail shell thing.
That's the one. The fluid movement makes these incredibly delicate sensory hairs called stereocilia bend or move.
Okay.
And when they move, they release neurotransmitters. Those excite the auditory nerve, which zaps a signal straight to your brain.
And the brain figures out what it means.
Instantly. It's an immediate, usually perfect conversion.
And this whole conversion process happens in this impossibly small, incredibly sensitive space. That was the part in the source material that just, blew my mind. The size of the cochlea.
It's minuscule. If you took a cross-section, the human cochlea is about the size of Lincoln's upper face on a U.S. penny.
It's just his face. On a penny. That small.
That small. And the total amount of fluid running this whole complex system, it's about 3 raindrops worth, maybe 140 microliters.
3 raindrops. That's it. Responsible for converting the entire world of sound into brain signals.
Pretty much, yeah.
That alone is incredible. But the sensitivity, we're talking movements at the level of atoms.
It is, scientifically speaking, the most sensitive sensory organ we have. It can detect displacements, movements, on the order of the diameter of a single hydrogen atom. That's sub-angstrom level.
It's hard to even grasp that scale.
Okay, try this. Think about a skilled violinist. When they move their finger just slightly on the string.
Tiny movements.
Right. If they shift their finger by just 1 micron, that's a millionth of a meter, that tiny change in string tension, your ear perceives it as a distinct change in pitch.
Wow, you definitely can't see a micron shift.
Not with the naked eye, no way. But your ear picks it up perfectly.
That level of precision must be amazing for survival, but like you said, that sensitivity, that must also make it really vulnerable.
Precisely. And then you add speed into the mix. Those outer hair cells, the ones that help tune and amplify the sound, they move incredibly fast, up to 20,000 hertz. That's 20,000 cycles per second.
20,000 times a second compared to what, like the heart?
Your heart beats at maybe 1 hertz, 1 cycle per second. So, we're dealing with a system that's constantly working at high speed and, well, it's highly exposed.
Okay, so when that system starts to break down, which happens, you mentioned there are sort of two main types, two buckets of hearing loss.
That's right. Broadly, you have conductive hearing loss. That's usually a mechanical issue, stopping sound from getting to the inner ear properly.
Like a hole in the eardrum, or those little bones getting stuck.
Exactly. Maybe they get frozen, can't move right. The good news there is that this type is often surgically treatable.
Okay, but then there's the other type, which is more common and more permanent.
That's sensory neural hearing loss. That originates inside the inner ear itself, in the cochlea or the auditory nerve.
And that's the tougher one.
Much tougher. Partly because the cochlea is buried inside the densest bone in the entire body, makes it incredibly hard to study directly, and often impossible to repair surgically, at least right now.
And that coiled structure, the snail shell, it's not just about fitting it in, is it? It actually determines vulnerability based on frequency.
Yeah, it's fascinating. If you could unroll the cochlea, different sign frequencies are processed in different locations along its length.
So like a piano keyboard, unrolled.
Kind of like that. High frequencies, and this is crucial high frequencies, where most of the important information in human speech lies, are processed right at the base of that coil, the entrance. Low frequencies are processed way down at the apex, the center of the coil.
Okay, so high frequencies at the beginning, low frequencies at the end.
Right. And unfortunately, that high frequency end, the base, is the most exposed part. It's the most vulnerable to damage from loud noise, certain drugs, and just the wear and tear of aging. It's usually the first part of the system to show damage.
So the very part we need most for understanding each other for communication is the part that gets hit first and hardest.
That's the unfortunate reality.
Yeah. Which leads us straight into the broader impact of losing that ability. Why is hearing just so critical for our emotional well-being, our cognitive health?
Because fundamentally, hearing connects us to people. Sight connects you more to things, to objects, the environment. Sound connects you to other humans.
Huh. I never thought of it quite like that.
You see it reflected throughout history, really. Socrates apparently said, "Speak so that I can see you," implying that speech reveals the person.
Interesting.
And Helen Keller, who obviously knew the difference intimately, she observed that deafness was a worse misfortune than blindness. Why? Because it separates you from people as opposed to things.
Wow. That really hits home. Separates you from people.
It's profoundly isolating.
And that connects directly to this idea you mentioned earlier, this hidden threat, especially for younger people. Hidden hearing loss.
Yes.
You might feel like your hearing's generally okay, pass a standard test even, but then you go into a noisy restaurant or a party.
And you just can't follow the conversation. You struggle badly. That's a key indicator.
So what's happening there? If the basic hearing test is normal,
what's likely happening first, before the hair cells themselves die off completely, is damage to the synapses. The connections between those sensory hair cells and the auditory neurons get destroyed.
Ah, so the connection breaks down first.
Exactly. Your threshold for detecting a sound might still be okay in a quiet room, so you pass the audiogram, but the quality of the signal being sent to the brain is degraded. It's fuzzier, less distinct.
Which makes it impossible to pick out speech and noise.
Precisely. Or you might develop new tinnitus, that ringing sound. The damage is happening at that connection level, the synapse level, long before the hair cell itself is totally lost.
And this all loops back to that really alarming statistic we started with. The strong link between hearing loss and cognitive decline, even dementia.
Right. When the brain is constantly having to work overtime, straining to decode a degraded signal, to fill in the missing auditory gaps.
It's using up resources.
It's a huge cognitive load. It diverts resources away from other important brain functions, like memory and executive function. It's essentially a constant drain.
And the economic cost of this is just mind-blowing, too.
It really is. The global economic toll of unaddressed hearing loss people who have it but aren't getting help is estimated to be nearly $1 trillion annually.
$1 trillion a year.
Yeah, this isn't some small niche health issue. It's a massive foundational global economic and health crisis that we're mostly ignoring.
Okay. We've definitely established the scale, the sensitivity, the damage potential. Let's shift gears into the practical stuff. What can we actually do right now to protect this incredibly sensitive system?
Absolutely. Actionable tools. Let's start with understanding safe sound levels, and that means understanding the decibel scale.
Right, the dB scale.
Yes. And the key thing to remember here is that it's logarithmic.
Logarithmic meaning
Yeah,
not linear.
exactly. A small number increase on the scale represents a huge exponential increase in sound power and therefore damage potential.
Okay, give us some reference points.
Sure. Typical conversation, like we're having now, is around 60 dB. A noisy airplane cabin might be 80 dB. A motorcycle roaring past or heavy city traffic may be 100 dB.
What concerts?
Clubs, usually 110, sometimes 120 dB or even more.
So because it's logarithmic, 80 dB isn't just a bit louder than 70 dB.
No, it's hitting your eardrum with way more energy, 10 times the power actually, for every 10 dB increase.
Wow.
And that leads us directly to the most critical safety formula you need to know. The rule of having time.
The rule of having time. Okay, what is it?
The basic guideline is this. 80 dB is considered safe for about 8 hours of continuous exposure.
8 hours at 80 dB, got it.
But here's the crucial part. For every 3 dB increase above that 80 dB level, you have to cut your safe exposure time in half.
Cut it in half for just a 3 dB increase. Okay, walk me through that.
Right, so 80 dB for 8 hours, go up to 83 dB, and your safe time drops to 4 hours.
Yeah.
Hit 86 dB, now you're down to 2 hours. At 89 dB, just 1 hour of safe exposure, and by the time you reach 92 dB, which is about the level of a loud lawnmower, you only have 30 minutes before potential damage starts.
30 minutes at 92 dB. And concerts are way higher than that.
Way higher, often 110 dBs or more. At those levels, the math shows your safe exposure time without protection is measured in just minutes, maybe even seconds.
Okay, that makes the case very clearly. Earplugs at loud events are not optional.
Absolutely non-negotiable. If you're going to a concert, a loud club, even some sporting events, you really need to be using earplugs, and not just any cheap foam ones.
Right, you need ones that actually reduce the level significantly.
Look for earplugs that offer at least 30 dBs of attenuation, of sound reduction, that can bring those dangerous 110, 120 dB concert levels down closer to that safer 80-90 dB range.
It seems obvious, but worth saying. Musicians wear them, right? People whose careers depend on their hearing.
The smart ones do. High-quality, often custom-molded earplugs. If they're protecting their livelihood, you should definitely be protecting your long-term hearing and brain health.
Okay, what about the danger that's literally right next to our ears all the time? Headphones and earbuds.
Yeah, a huge source of potential damage, especially with chronic exposure.
What's the simplest way, the most intuitive check for someone listening? How do you know if it's too loud?
It's really just the common sense check. Can anyone standing near you hear what you're listening to through your headphones or earbuds?
Ah, the sound leakage test.
Exactly. If they can hear it, even faintly, it is almost certainly too loud for safe, extended listening. You're exceeding safe limits.
Good rule of thumb. And especially important for kids.
Definitely. Parents need to be really mindful. Children's auditory systems are generally more vulnerable to noise damage than adults. Keep those volumes down.
Okay. Switching from external protection to internal. Nutrition. The source material we looked at highlighted magnesium.
Yes, there's actually pretty strong evidence for magnesium, particularly in preventing noise-induced hearing loss. A lot of this comes from studies involving, say, military personnel.
Where they have mandatory noise exposure?
Right, like during weapons training. And they found that magnesium levels seem to play a protective role. In fact, after a noise trauma event, magnesium levels inside the inner ear fluid, the paralymph, are one of the things that changes the most.
So the body is clearly using it or needing it in response to noise.
Seems that way. It appears to be essential for protection and recovery in the inner ear.
So if someone wanted to supplement, is there a particular type of magnesium that's best for this?
Well, first, getting it from your diet is always ideal. Think seeds, nuts, fatty fish like salmon, green leafy vegetables like spinach, lots of good sources. Yeah. But if you're looking at supplementation specifically for sort of neurological or inner ear protection, magnesium L-threonate is often suggested.
Why that one?
Because it's known to be particularly good at crossing the blood-brain barrier and likely the blood-cool-clear barrier too, so it gets where it needs to go more efficiently.
Interesting. Okay, another tool. Medication awareness. This one surprised me because it involves really common drugs.
Yeah, this is important. We need to talk about NSAIDs, non-steroidal anti-inflammatory drugs.
Like ibuprofen, acetaminophen.
Exactly. Ibuprofen, naproxen, even acetaminophen, which isn't technically an NSAID but often gets lumped in. Regular intake of these.
How regular is regular?
The studies generally define it as at least twice a week on a consistent basis.
Okay, so taking them twice a week or more.
Significantly increases your likelihood of developing hearing loss.
Wow. That affects a lot of people taking it for chronic pain or headaches. Is that damage permanent?
The good news here generally is no. This specific type of medication-related hearing loss is often reversible once you stop taking the medication regularly.
Okay, that's reassuring.
But it definitely highlights the need to be cautious about chronic long-term use of these everyday pain relievers. Maybe talk to your doctor about alternatives if you're taking them frequently.
Good advice. Okay, last tool. This one's about communication. How to talk to someone who already has some hearing difficulty. Our first instinct is usually just to shout. Right.
Right. And it's often the worst thing you can do. Because just increasing the volume, yelling, often distorts the sound even more, especially if they have sensory neural loss. It can make the words less clear, not more. It might even be painful.
So what should we do?
The golden rule is simple, really. It's much more important to face them directly so they can see your lips and facial expressions.
Lip reading cues.
Exactly. And slow down your speech just a little. Don't exaggerate it, but speak clearly and slightly slower. That combination of visual cues and slightly slower pace is usually far more helpful than just shouting.
Face them and slow down. Okay, let's shift to a related topic that impacts, nearly 50 million Americans?
Tinnitus.
Yeah, that phantom ringing, buzzing, hissing sound.
What is actually going on in the brain when someone experiences tinnitus?
Fundamentally, tinnitus is the brain generating a sound that isn't actually there externally. It's a phantom perception.
Like phantom limb pain. Exactly the same neurological principle. It typically happens when the auditory centers in the brain notice a reduction in the normal input from the ears, maybe due to hearing loss, even subtle loss. The brain essentially notices the silence or the change and tries to fill the gap by creating its own noise.
So the brain is making it up because it's missing the real sound.
That's the leading theory, yes. It's hyperactivity in the auditory cortex compensating for lost input. But tinnitus is also tricky because it's an umbrella term. Lots of different underlying causes can lead to that symptom.
I know so many people try supplements, diets, everything for tinnitus relief. What does the actual science say about treatments right now?
Yeah, the reality is pretty tough, unfortunately. Despite tons of anecdotal reports and things you read online, large systematic reviews of studies currently show no consistent, reliable benefit from general supplementation for tinnitus.
So the magic pill isn't there yet?
Not really, no. The evidence-backed interventions focus more on managing the perception and impact of the tinnitus.
Like what?
Two main things stand out. Amplification, meaning hearing aids, if there's underlying hearing loss.
Because that restores some input.
Exactly. It gives the brain more real sound to process, which can sometimes reduce the brain's need to create the phantom sound. And the other big one is cognitive behavioral therapy, CBT.
Therapy for tinnitus. How does that work?
It helps people change their reaction to the tinnitus. Remember, the brain is the organ of intervention here. When you focus on your tinnitus, worry about it, get anxious about it,
You're amplifying the signal.
you are literally strengthening the neural circuitry associated with it. CBT helps you learn techniques to redirect your attention, reduce the anxiety, and essentially teach the brain to tune it out to make it less intrusive. Distraction is neurologically key.
So it's about retraining the brain's response.
Absolutely. And the power of the brain's plasticity, its ability to change, is really where the hope lies.
And the most compelling evidence for that plasticity, for the brain's ability to fix this, actually comes from cochlear implants.
Right. It's really remarkable evidence. Cochlear implants are used for people with profound deafness. They bypass the damaged inner ear and directly stimulate the auditory nerve, sending corrected high-quality sound information to the brain.
So they fix the input problem.
Precisely. And what they found in these patients, many of whom also had severe tinnitus before the implant, is stunning. In about 10% of cases, the tinnitus resolves completely after the implant, just gone.
Wow.
And in maybe 75% more, it improves significantly.
That's huge.
It's powerful proof. If you can restore or correct the peripheral input, give the brain the sound information it's supposed to be getting, the brain can often recalibrate itself and shut down that phantom noise circuitry.
That's an incredible demonstration of brain adaptability, even in the auditory system. Amazing.
It really is.
And just briefly, we touched on it earlier, but hearing and our sense of balance are deeply connected systems, aren't they?
Oh, yes. They co-evolved. Both the auditory system and the vestibular system, our balance system, are located right next to each other in the inner ear, and both fundamentally sense vibration and movement.
Same basic mechanism.
Right. And it's worth remembering auditory neurons are some of the most metabolically active neurons in the body. They're constantly firing hundreds of times per second, processing this vibrational information. It's an incredibly busy, sensitive system designed for detecting movement.
Okay, let's try and bring this all together then. Let's crystallize the key takeaways for you, the listener.
All right. First, just respect the incredible sensitivity of your ears. They're working at an atomic level.
Yeah.
Second, internalize that rule of having time. Remember, 80 dBs for 8 hours and halve the time for every 3 dB increase. That logarithmic scale is key.
Use good earplugs, quality ones, with decent attenuation, especially for concerts or loud venues.
Definitely. Consider magnesium, either through diet or perhaps magnesium thrownate, especially if you know you'll be around loud noise. Be mindful of regular NSAI use.
Right. And finally, those communication adjustments. Someone's having trouble hearing you.
Don't just yell. Face them and slow down your speech a bit. That helps way more. It protects your connection, your social life, which is tied to your cognitive life.
Okay. And to leave you with one final thought to chew on, something building on that connection between hearing and balance.
Yeah, that shared sensitivity to vibration.
Since the body registers all kinds of vibration, not just sound waves we hear, think about how constant low-frequency noise might be affecting you.
Things you might not even consciously register as sound, like maybe loud bass thumping from next door, or even just the constant rumble of traffic or industrial equipment nearby.
Right. Could that constant non-auditory vibration be creating a kind of background stress? Could it be interfering with your balance system, your nervous system, maybe even your emotional state in ways we don't fully understand yet?
It's an interesting question. How is that constant vibrational energy impacting us physically and neurologically, even if we aren't hearing it in the usual sense? It's definitely an area that's ripe for more exploration.
Something to think about. Thank you for joining us for this deep dive.